All right, so we're going to move along here. I do want to mention, and I certainly don't want to gloss over the Boyle's Law, and I will have a few more slides, a couple more videos on actually using and solving those PV equals PV, and then some of these other laws that are coming up. So take a look at that later on in the unit and later in the chapter. I do want to move now to the next law. The next gas law is Charles's law. Charles's law. First, let's introduce ourselves to Jacques Charles. Jacques is a Frenchman, late 1700s. Don't hold it against him, hence my last name. Charles was the first person to make a flight in a hydrogen balloon. 1783. Pretty impressive. Again, noticing different temperatures and volumes. You'll see as we move along with what his law is, why it makes sense that he made the first flight in a hydrogen balloon. Anyhow, Charles's law deals with if the pressure remains constant. Notice that in Boyle's law, the temperature was constant. Charles's law, if the pressure remains constant, as the temperature increases, the volume also increases. Boyle's law was an inverse relationship. As one went up, the other went down. Charles's law is a direct. As one goes up, the other also goes up. Here's an example. Notice that our pressure is constant. Okay, so pressures are the same. Pressure is constant. Okay, and here, if we look at our temperatures, as we heat it, so we increase our temperature, okay, the molecules are moving around a little faster. Because there's no change in pressure on the exterior of this container, the molecules are moving around faster. They're slamming up against the lid, I guess you could say, the covering of this container. And so because they're moving faster, they're expanding the volume. And please note that if you double the temperature, you're also going to double the volume. Okay, so doubling one will also double the other. Just as if we decrease one, if we decrease the volume, then you would decrease the temperature, you could decrease the volume. The molecules aren't moving around as fast. Okay, so that's Charles's law in a nutshell. Let me show you a little bit about that, and then I have a video to show as well. But, so Charles's law is this. Let's say we have volume is 0.5 liters. My temperature is 200 K. That's in situation 1. All right. In the second situation, which is this one over here, the volume is now 1 liter and the temperature is 400 K. All right. Now, if you multiply those, 0.5 times 200, you get 100. So it's not a V times T situation. What it is V1 over T1 is going to be equal to V2 over T2. If you take 1 and divide it by 400, you would get 0.0025. The same thing if you take 0.5 divided by 200. So Charles's law is this. The V1, the first situation volume, over the T1 is equal to the V2 over the T2. All right? So as you increase the temperature, you also increase the volume. That direct relationship. Now, I want to just quickly solve for one of these, and I think it's pretty easy if I do this. Let's say I want to solve for this V, okay? And I'm going to call these my V1s and T1s, and this is V2, T2. And here's my formula right here. V1, T1 equals V2, T2. I'm a huge fan, okay? We're solving for V1. Let's say that we don't have that 0.5, and we've got to solve for it. I'm a huge fan of getting rid of any denominators, any fractions, and cleaning it up. How do you clean it up? How do you get rid of any fractions? How do you get rid of any denominators? Cross multiply. If you cross multiply, V1 T2 is equal to T1 V2. That red formula is the same as the black one, which is Charles's law. V1 over T1 equals V2 over T2. So by cross multiplying, I now have no denominators, which then allows me, if I'm solving for V1, I could divide both sides by T2, and my formula for V1 is T1 V2 over T2. Okay? And now, if I wanted to solve for V1, like I said I was going to do, if I take V1, if I take T1, which is 200, and I take V2, which is 1 liter, all I'm doing is plugging into this formula that I have right here, my T and my V, and divide that by 400, okay? Notice that V1, 200 times 1 is 200. Divide that by 400, you get 0.5. My units of Kelvin cancel, and I would get liters. And that is indeed what we had earlier for the volume. So again, I'm a really big fan. Here's my Charles's law. I'm going to write it again. Charles's law is V1 over T1 equals V2 over T2. But I'm a really big fan of getting rid of any denominator stuff. V1 T2 equals V2 T1. We didn't have to worry about that with Boyle's law because everything was all in the numerator. There's no denominators. And you could solve for any of these four by just dividing whichever one on that is next to it on that side. Okay? We're going to be doing a lab in class, but I just want to mention, you know, I have a balloon right here, and I can determine its circumference very easily. I could determine the volume of this by knowing the circumference, by knowing the diameter, by knowing the radius, and then using 4/3 pi r cubed to get the volume. But I just measured around the balloon in a certain circumference, okay? And I've got a little bit of trouble here. You know, somewhere in the range of 190 millimeters, okay? I've got two, if I can do this here with such, I don't have a lot of room, but I've got two beakers that I have set up. I've got one beaker that's ice water, and I have another beaker that I heated up. Okay, this one's reading around 50 degrees right now. If my balloon's circumference was 190 millimeters, 19 centimeters, if I plunge this into my ice bath now, because I'm going to drop the temperature, okay, the volume will also drop. And I could leave that in there for a little while, but let's see if I got any kind of dropping of my volume, my circumference, which again is in turn my volume. Let's see if that worked, if I kept it underneath long enough. My string is starting to stick together. But basically, come on, I'm at around 18 or 180, right about there, 180. So it's dropped a fair amount, okay? I now could certainly plunge it into my 50 degree water, plunging it in here. And you can actually see, I don't know if you can actually see, I mean obviously besides refraction, but you can see that the balloon is significantly larger than it was before we put it in. And if I'm quick enough here, this is a lab I'll do with my students, if I'm quick enough I can wrap it up and let's see again here. We should have a longer measurement here. And yeah, you can see I'm kind of at around, maybe you can see, around 20 or 200 centimeters. So I didn't leave the balloon in for very long, but basically I can increase or decrease the size of my balloon, the volume, not by blowing any more air into it, but rather by changing the temperature. Okay? I have a little video to go with that as well. So here's Charles's law, and here's a quick little video. Whoops. I'm going to have to erase. Oh, I think I'm okay. It's a little demo that Bob Burke performed here.
So So let's be a little quantitative here. Suppose we take a sample of gas at 1 atmosphere pressure and 25 degrees C, and it's got a volume of about 1 liter. So I brought something here we can do this with. Your average latex glove. Hopefully it doesn't have any powder on it. I hate powdered gloves. So we'll use this as that's about 1 liter, I guess. And the gas in here is, so much for that. Sharp nails, I guess. The gas in here is just air. Note that it doesn't make any difference what the gas is because Charles' law applies equally to all gases. This better work because I only brought 2. If you think tying balloons is hard, you should try one of these suckers. Oh man, I'll be able to do this. So I'll talk while I do this. So what I'm going to do is trap some gas in this balloon. It looks like about 1 liter that I have in here. And I'm going to change the temperature, and we're going to observe a change in volume, hopefully, which will coincide with what Charles' law tells us. You know, when you get your little finger stuck in the hole there, there we go. There we go. This thing's really tough. Okay, so that's about 1 liter of air stuck in this balloon. Now, suppose you did the following experiment. Suppose you were to cool it to minus 196 degrees C. How are you going to do that? Well, minus 196 degrees C just happens to be the boiling point of nitrogen, so you could do this by pouring liquid nitrogen on it. So put this under the camera here. There we go. So I've got it sitting in another Dewar flask, so I can pour the liquid nitrogen over this, and some of it will fall inside, and we'll see what happens to the volume of this thing. First of all, the rubber gets kind of brittle, so sometimes it goes bang. You can probably see better from where you're sitting that this is shrinking than from the camera angle. Okay, so I've cooled the gas that's in there to minus 196 degrees C, so according to Charles' law, it should shrink, and it did, of course. There's just as much air in there as there was before, but the volume has shrunk considerably. And if you look, if I can show this under the camera, if you look under the camera there, you might be able to see down here, I can see it quite clearly, but I don't think it'll show up on the camera, that we've actually managed to liquefy some of the air that was in the fingers of this.
You can see that obviously I don't have any liquid nitrogen on me, but by pouring the liquid nitrogen, dropped the temperature of that gas inside the balloon, and so therefore the volume dropped quite a bit as well. So that's Charles's law. We'll use some formulas and we'll calculate with it in a moment.